Welcome to Mr. Pratt's Physics. Today, we're going to figure out how much kinetic energy an object has. What is the equation that tells us how much kinetic energy there is? In order to do that, we're going to use this ramp here. And we're going to make use of a number of these springs here. Well, we've already figured out the equation that tells us how much energy is stored in a spring that is either stretched or compressed. We know that's 1/2 kx squared, where x is the amount that the spring is stretched and k is the spring constant. We're now going to use that information to impart some energy into a cart by having the spring push it along. The energy from the spring will be transferred into the cart. We'll be able to determine the equation that tells us how much kinetic energy is in the cart. To get started, I've got a ramp set up here, and I've carefully made sure that it is a flat ramp so that we won't have this going up or down, causing a change in gravitational energy. So the only energy we'll have to worry about is the energy in the spring to start with, and then the energy in the cart as it moves along. We'll do that like this. I'll have this cart and the spring, and we'll have the spring set up so that I will have it at a certain level where I know how much energy is stored in the spring. Then I will release the spring, causing it to push the cart, and when it pushes the cart, there will be a kinetic energy involved in that cart. We'll be able to determine the relationship between the energy in the cart and the velocity of the cart as it moves down the ramp. You can see that I've made a number of marks along the ramp here. These are spaced at 10 centimeter intervals so that as the cart moves along, we'll be able to time that and determine how fast the cart is actually going. Now I'm going to start with this blue spring. I know it has a spring constant that's approximately 2.5 newtons divided by 0.05 meters. So I'm going to compress this spring approximately 5 centimeters so that when I release it, the cart ends up with some kinetic energy based on the amount of elastic energy that was originally stored in this spring. Now there is a little bit of friction in that cart, but hopefully not so much that it's going to bother our results too much. Let me try a different spring. This spring is a little stiffer. It has a spring constant that's approximately 5 newtons divided by that 5 centimeters. And so when I compress this by that 5 centimeters, when we go ahead and release the spring, we've given it some velocity. We can relate that velocity to the amount of energy stored in the spring. Let's do that in slow motion. This spring has a spring constant of 10 newtons divided by 0.05 meters. Now, I have previously measured the mass of this cart. It turns out it comes out to 0.292 kilograms, 292 grams. And as any good experimenter, I'm going to take a number of measurements for each experiment so that I can easily detect whether I have a problem with one of my measurements, whether from the not releasing the spring properly or perhaps some other issue, and I'll be able to average out my values so that I have good data that I can be confident with. Wow, that was a lot of data, painstakingly gathered. I had to practice my technique on how to release that spring in a consistent manner and somehow pay close attention to just how much I was actually pulling that spring out before I released it. Those early springs, the blue one and the green one, were not too difficult because they weren't real stiff springs, but boy, by the time we got down to those last ones, it was really hard work to try to find a way to do that consistently so that I would get consistent results and have data that we could trust. After all that hard work, I was really pleased with the results though. As hard as it was, I was able to get some consistent results. I used the video to be able to determine what the speeds were. Of course, I'm not showing all that data in one video here. So with all that hard work and those results, let's take a look at what they actually say. So here's my data table. I've got this written actually with the velocity in the left-hand column and the energy in the right-hand column. Even though in real life, really what I did was this was my independent variable, the amount of energy that we started off with as elastic energy, but which ended up as kinetic energy. Usually our independent variable is going to be in our left-hand column, but this time I put it in the right-hand column because what I want to graph is the energy on the vertical axis and the velocity on the horizontal axis to try to get the relationship between how the velocity affects the energy in a more traditional way of graphing this data. The velocity on the left-hand side are dependent variable, and you can see that when we started out with an elastic energy, which therefore was transferred into that kinetic energy storage mode, we had 0.06 joules of energy, and the velocity of my cart ended up as about 0.7 meters per second. With one of the other springs, and I ended up with 0.13 joules of energy. The velocity of the cart was 0.90 meters per second. Going on down the line, when my energy was about 0.4 joules, I had 1.6 meters per second of velocity. And on going down here, we see these various values as I continued down to an initial elastic energy, which then became our kinetic energy of 0.75 joules. The velocity of the cart was 2.3 meters per second. I also put 0, 0 here because if we started off with 0 energy, of course it's not going to make the cart go anywhere. So the cart would also have a velocity of 0 meters per second. So in your assignment, you'll be graphing this data of energy versus velocity. You'll see what that relationship looks like. you're going to find that it's not a straight line. You'll know the methods you can do to this data to graph it, to linearize the graph in such a way that we will have a straight line and be able to determine the relationship between the kinetic energy and the velocity of the object. Good luck and have fun.